What's up everybody? Welcome to my latest video in my data analysis and statistics series. What we're going to do today is we're going to look at how to use a graphing calculator to analyze normally distributed data. If you missed the last video, make sure you go back and watch it. That previous video is about normal distribution curves. It's more of an introduction to them and how do we analyze data. Let's jump right into it today. When we left off last time, we talked about some properties of a normal distribution curve that we should probably review. First thing that you should know is that the labels on the bottom stand for the numbers of standard deviations away from the mean. We know that all of the data will fit under the curve. We know that 68.2% of the data will sit within one standard deviation of the mean. We know that 95.4% of the data sits within two standard deviations of the mean. And finally, 99.8% of the data lies within three standard deviations of the mean. When we looked at our last video, everything fell nice and perfectly on either one standard deviation away, two standard deviations away from the mean, or maybe even a half a standard deviation away from the mean. Today we're going to look at the scenarios where what happens when something doesn't fall perfectly on one of these grid lines that we see at the bottom of this curve. What can we do then? And the answer is we'll use a calculator. The formula that we're going to use in the calculator is known as the normal cumulative density function, which I'll be abbreviating NormalCDF. Essentially what this does is it will find the probability that some variable falls in the interval you supply. Let's say you want to know what's the probability that a temperature in San Francisco is going to be within 60 to 67 degrees. You could type that information into the calculator and it would tell you what the probability was. What you need to know is the left value on your curve. You need to know the right value on the curve. Sometimes those are referred to as the lower value and the upper value. And of course, you need to know the mean and standard deviation. A couple things to keep in mind is sometimes you might not know the left value on the curve. Let's say someone says, what's the probability that a temperature will be at most 75 degrees? Well, I know the upper value will be 75 degrees, but in that scenario, I don't know the lower value. So what we're just going to do is if we don't know the lower value, we're just going to input negative 999,999, just because it's an incredibly small number that will encompass all of the numbers that would be lower than really anything. Similarly, we could be missing the upper value or the right value. In that scenario, we're going to input the right value as close to 1,000,000 or 999,999. Again, the reason is if I don't know that upper value, we're just going to use an incredibly large upper value that will encompass everything that would come up all of the time. And one other thing to note that won't affect us today is sometimes this formula is different depending on your calculator. I know personally that if you use a Casio 9750 G2, it does this calculation a little backwards. Specifically, it replaces the mean and standard deviation in opposite spots. Not something that's going to affect us today, but something to keep in mind of. Let's do a problem together. Here we're talking about the lifespan of a 60-watt light bulb produced by a company that's normally distributed with a mean of 1,450 hours and a standard deviation of 8.5 hours. What we want to know is if we select some random light bulb produced by this company, what's the probability that the lifespan will be somewhere between 1,440 hours and 1,465 hours? First thing I like to do here is set up my curve. I like to put things on the curve, see where they lie. Start by placing below 0 the mean. In this case, the mean is 1450. Now we'll use that standard deviation of 8.5 to add and go above. Well, if I add 8.5 to 1450, I'll get 1,458.5, and I could continue this pattern. I could also subtract 8.5 from the mean to get the values below. Well, if I'm looking for between 1440 and 1465, you'll see those values don't fall here perfectly on the curve. Those values generally would be here. I want to find what percentage of data that is, and using this normal distribution curve won't work, so we're going to use the calculator. I want to bring up this function here. All I need to know is the left value, the right value, the mean, and standard deviation. Well, the left value here is this value to the left, which I can see in the problem is 1440. The right value is this value here, which I want to calculate up to 1465. The mean was given at 1450 with a standard deviation of 8.5. I plug that into the calculator and we find out that the probability is about 0.8414, which is about 84%, which is choice C. So let's talk about how you can use this NormalCDF function on your computer at home. First thing you're going to want to do is open up deltamath. When you're on deltamath, what you're going to do is go up to the top right-hand corner and select Statistics Calculator. From there, what you're going to do is you're going to go to Distribution. When you're on the Distribution menu, what you're going to have to pick is NormalCDF. You'll see it has a space for lower, upper, mean, standard deviation. Simply type in the values you want, hit Calculate, and voila, there is the probability written as a decimal that a value falls between your lower and upper value. In this problem, we're talking about someone that's commuting to work and the amount of time that it takes them to arrive. If the amount of time it takes them to get to work has a mean of 41 minutes and a standard deviation of 2.5 minutes, what percentage of those commutes will be shorter than 39 minutes? Here we want to bring up our blank curve. To me, this helps me kind of get centered in the work that we're doing. Below 0 is where I'm going to place my mean. Here the mean was given at 41 minutes. Then I look above and below. With 2.5 minute standard deviations, I could continue to add 2.5 to get these values here. Similarly, I could subtract 2.5 from 41 to get the values here. Now in this problem, we want to find the percentage of the commute that's shorter than 39 minutes. 39 is going to be somewhere between 38.5 and 49. So here's 39 somewhere here. Now if I want to find the percentage of the commutes that are shorter than 39 minutes, I need to go to the left of 39. So I'm really looking for the percentages here. What I'm going to use is the calculator, and I'm going to use this NormalCDF function. I need to know what the left value is. Well, recall that we don't know what the left value is here, and realistically what we're going to do is if we're missing that left value, we're just going to replace it with negative 999,999. My right value is the uppermost value I'm going to reach, which in this case is 39. My mean is 41 minutes, and the standard deviation is 2.5 minutes. We'll plug those in. Typing that in the calculator gives me this value here. And if I look here, what they want me to round to is the nearest tenth of a percent. Right now this is a decimal. In order to make it a percent, I simply multiply by 100, which moves the decimal place 2 spots over. Now I want to round to the nearest tenth. When rounding to the nearest tenth, I highlight the 10th digit and then decide based on the digit that follows, should I round that one up or keep it the same. In this case, because the 8 is a 5 or higher, I'll make this 21.2%. Which means that the amount of time she spends on her commute that would be shorter than 39 minutes would be 21.2% of the time. Let's see if you can try one of these problems on your own. This problem reads, at Chipotle, the amount of time that customers have to wait for their food is normally distributed with a mean of 8 minutes and a standard deviation of 1 minute. What percentage of customers have to wait between 6 minutes and 8.5 minutes? Round your answer to the nearest hundredth. First thing I want to do here is sketch a blank normal distribution curve. You can do this on your own paper. It's very simple to do. Now what I want to do is place the mean below 0. The mean here is 8 minutes. Now use the standard deviation of 1 minute to find values above and below. 1 minute more than 8 would be 9 minutes. 1 minute below 8 would be 7 minutes, 6 minutes, and so on. I want to find what's the average wait time between 6 and 8.5. So I'm going to shade here. Now I can bring up my formula. My left value is the lowermost value I want to find, which in this case is 6. The right value or upper value is going to be 8.5. My mean, we already said, was 8 with a standard deviation of 1. Plugging this into the calculator, I get 0.6687124, and rounded to the nearest hundredth, this 6 is the hundredth place. So I look at the value after 6 and decide, should I round that 6 up or keep it the same? Because the 8 is larger than 5, or greater than or equal to 5 really, we're going to round that 6 up to a 7. Our final answer is 0.67. What this means is that 67% of the time, a customer at Chipotle would wait between 6 minutes to 8.5 minutes for their food. Let's try this example about bowling. Here we have some bowling scores that are normally distributed with a mean of 120 and a standard deviation of 11. What percentages of the games will be scored higher than 116, rounded to the nearest tenth of a percent? Well, first thing I want to do is sketch this blank normal distribution curve. Of course, below 0 is where we're going to place the mean. The mean here is 120. Then we use the standard deviation of 11 to fill in a little bit more of this curve. Here we'll put 11 more than 120 is 131. 11 less than 120 would be 109. And what we want to do is find the percentage of games that she scores higher than 116. If I go ahead and I think about that, 116 is probably about here. And I want to find the percentage of games that are higher than that. So I'm talking about all of this region in here. This is really what I'm interested in finding, is what percentage of games are higher than 116. So I'm going to use my formula here. What I have to think is, what's the lowest most value? The lowest most value here is going to be 116. The highest most value, I really don't know. Sure, in a game of bowling, the highest score you could receive is 300. But what I want to do is just have some uniform system. So if I go back to my formulas, what we said is that if we're missing the right value, we're just going to automatically use this value here, 999,999. So that's what I'm going to use here. My right value, I'm not going to use 300. I'm just going to use that enormously large number. Our mean is 120 and our standard deviation is 11. We plug those in. Now what we need to do is just type it into the calculator. We get this value here. They want it as a percentage, so we multiply by 100, or just move the decimal 2 places. Now we need to round this to the nearest tenth. If I look at the 1, that's the 10th digit. I look at the 9 and decide, is this greater than or equal to 5? It is, so I'm going to round the 1 up rather than keep it the same, and I get 64.2%. Let's try another problem. This problem reads, in 2013, approximately 1.6 million students took the critical reading portion of the SAT exam. The mean score, the modal score, and the standard deviation were calculated to be 496, 430, and 115 respectively. Which interval reflects 95% of the critical reading scores? Well, there's 2 ways to do this problem. Let's first talk about how we could do it using our calculator, kind of like we have. The first idea is to realize that all of these answer choices here represent intervals. They're just using plus and minus notation. So if I use the plus and minus, I could actually find the intervals, meaning to find the interval for part A, you would subtract 115 from 430 to get the lower limit and add 115 to 430 to get the upper limit. Similarly, for choices B, C, and D, you would take the second value and subtract it from the initial to get the lower value and add it to get the upper. If you did, your intervals corresponding to each answer choice would look like this. Now what you could do is you could bring up your formula and just type in the different left values, the different right values with the mean and standard deviation. Looking at this problem, there's a lot of extra information we don't need. We don't need the year 2013. We don't need to know how many students took the exam. Further, they give us the mean, modal, and standard deviation. I certainly don't need the modal, so I won't need 430. I just need the mean of 490 and the standard deviation of 115. When something says respectively, that means that the order that the information presented is the same as the order of the information presented down here. Meaning they gave the mean, then the mode, then the standard deviation. So down here, this represents the mean, then the mode, then the standard deviation. If I was to plug all of these into the formula, the only one that would work here is the one where I started with 266 as a lower value. My upper limit was 726, standard deviation, or rather mean of 496, and a standard deviation of 115. It looks like that answer choice would be choice number 4, or choice D. There is another way to do this problem. The other way to do this problem is to realize that this 95% is not arbitrary information, but it should be a number that you kind of should recognize. Well, if I go back to the general definition of the normal distribution curve, I can see where that 95% lies. That 95% represents data that lies within 2 standard deviations of the mean. So if I go back and think about this problem, I can think about what each of these numbers represent. Well, 430 was the mode. 115 was the standard deviation, 430 again was the mode. 230 is now 2 standard deviations. 496 is the mean. 115 is 1 standard deviation. 496 again is the mean, and 230 is 2 standard deviations. So I have this information here. Of course, when we look at it, there's no such thing as taking the mode and adding 1 standard deviation or subtracting it. And if we think about this curve, what we learned is that 95% of the data lies within 2 standard deviations of the mean, so the interval that does that is choice D. This one here, choice C, would have represented about 68.2% of the data, which is not what we're looking for. Let's try one final example. In this final question, we're talking about the weights of bags of chocolates that are normally distributed with a mean of 4.3 ounces and a standard deviation of 0.05 ounces. If this is true, what's the probability that a bag of these chocolate candies weighs less than 4.27 ounces? In order to do this, I'm going to start by drawing this blank normal distribution curve. First thing I'll do is below 0, I'll put my mean. Then I'll start to add 0.05 to find the values above and below. I want to find the probability that a bag of these chocolates weighs less than 4.27. 4.27 is probably right about here. So I'm going to shade to the left because I want the values less. I'll bring up my NormalCDF and I'll plug in the left value. Because we don't know the left value, I'm just going to plug in negative 999,999. The right value here is going to be 4.27. The mean was given at 4.3 and the standard deviation is 0.05. Plugging this information into the calculator, I get 0.2743, which is choice B. I hope you enjoyed this video, and I hope it helped you find the probability that a variable falls in any interval you supply using a graphing calculator. Until next time.